Hello students, in today's lecture video, we will discuss about a topic called computability of algorithms under design and analysis of algorithm. Myself, Sasireka, assistant professor from Computer Science and Business System Department from RMD Engineering College. We'll move on to the topic called computability of algorithms. So from the unit 1, we discussed about what is an algorithm, what are the different characteristics of an algorithm, what are the rules we have to follow in order to write an algorithm. And we also discussed the sample algorithms regarding Fibonacci of to find Fibonacci series, factorial of a number, sum of n natural numbers. And we have also written algorithm related to searching and sorting, right? So now we have to come into the topic called computability of algorithms. Okay. So this algorithm, this computability is considered about what are the ability to solve the problem in an effective manner. Okay. So the computability of a problem is closely linked to the existence of an algorithm to solve the problem. So there are divided, there are different algorithms are there. The algorithms are divided into various parts. So different parts are P class, NP class, NP complete, and NP hard. So let us discuss deeply about what are these classes of algorithms. Okay. So this is a pictorial representation of how the classes are defined. Okay. So whenever we have a P class algorithm, that means why we are writing an algorithm is used for solving a particular problem, right? So that is why we are writing an algorithm. Okay. So whenever we have a problem, for that we need an algorithm, that the solution will be given in the form of algorithm. Okay. Then we can able to give that algorithm the form of pseudocode. Then pseudocode will be converted into any programming language. Then we can able to find a solution with the help of computer. So this is what the basic characteristics of algorithm we discussed in the unit 1, and we discussed so many algorithms also, and we discussed so many problems. Now coming to the end, what about the class an algorithm is belongs to? If your algorithm is belongs to a class called P class, properly class, then it is easy to solve and easy to verify. Okay. Say for an example, if you have a sorting algorithm and searching algorithm, these are algorithm. This algorithm will be obviously required some polynomial time. Okay. So whenever your algorithm which takes some polynomial time to execute, then it is a P class problem. Okay. Coming into the NP, NP means it is not, we cannot able to determine an algorithm specific time execution. Okay. So that means this algorithm, NP class algorithm, will take some polynomial, apart from polynomial time, it will take some exponential time in order to execute the algorithm. Okay. So these are some problems which is very hard to solve. If you take an example in second unit, we discussed about the traveling salesman problem, a knapsack problem, like assignment problem, a graph coloring problem. So many problems we discussed, right? So these are some of the problems which take some exponential time. So during that also we discussed what are the time complexity of those problems, right? So whenever your algorithm will take some polynomial time, so we can able to specifically mention some time complexity, that algorithm will call it as P class algorithm. Okay. So P class stands for polynomial class algorithm. NP means non-deterministic polynomial class algorithm. So this is hard to solve. This will take some exponential time to solve your particular problem. Say, but what is the specialty of this NP problem is, whenever we have an NP problem, it is easy to solve. But when you have a solution for that NP problem, but we can verify those solutions within polynomial time. So that is a specialty of NP hard problems. Okay. So we'll see. So and one more thing, P class problems are always tractable problems. We know what is the time complexity. This because obviously this will require some polynomial time. So these are always tractable. What we mean by the polynomial time is the time which is required less than your exponential time. So we have the order of time complexity we discussed in unit 1, right? So start with your time complexity, linear time complexity, constant time complexity, some logarithmic. So these are the time complexities which will come under lesser than your exponential time. So these type of problem we are calling it as polynomial class problem. So these problems are tractable always. Apart from this NP hard problem, these are intractable problems. We cannot determine the time complexity. It will take some exponential time. In some cases, it will take some infinite amount of time also for execution. We cannot predict the time. So obviously, this will take some exponential time. But the specialty of NP hard is the problem solution has been given for NP hard algorithms. Then it is easy to verify the solution. Solving takes exponential time, but verifying the solution will take some polynomial time. So this is a relation between P and the NP class problems. So basically, our algorithm is classified into two types: P class and NP class. In NP class, we have it is subdivided into two more classes. That is NP hard and NP complete. So what is this P class problem? As we discussed, these are the problem which takes some polynomial time. It is known as P class algorithm. Say for an example, sorting and sequential algorithms. So you can see insertion sort will take some order of n square time, and merge sort is taking order of n log n time, and sequential search is taking an order of n time. So these sequential, these time complexity we already discussed how we have to calculate the best, worst, and average case time complexity in unit one itself, right? So an algorithm is said to be solvable in polynomial time if the number of steps required to complete the algorithm for a given input is always order of n to the power k. So it will not execute, it will not exit. Okay, this is always the n carries positive integer. Okay, and in n represents the time complexity of your input. Moving on to the P class, as we already discussed, these problems are also always tractable. While other problem apart from polynomial time, there are intractable or super polynomial problem. So in the worst case, this algorithm will always take order of n to the power k. In the worst case, I'm not talking about the best. Best means where you can get linear or some constant time also. In the worst case, this algorithm will go beyond, it will not go beyond order of n to the power k. So this class algorithm, we are calling it as polynomial class algorithm, where k is a positive integer value. And moving on to why polynomial. So these are the algorithm comparison, the order of algorithm we have discussed already. Whenever you are giving the value of n, we can able to calculate the logarithmic n log n to the power 2 n square. So these are the time comparison which is given based on the value of n. Okay. And the order of growth, various classes for expressing efficiency of an algorithm. Whenever your algorithm is taking some linear, some constant time, though that is constant time algorithm, if it takes logarithmic n, logarithmic algorithm, if it takes order of n, then it is linear. Order of log n, it will take logarithmic type, quadratic, cubic, exponential, factorial. At last, worst case, you'll be getting the time complexity as n factorial. Moving on to the NP class, this is not deterministic polynomial time algorithm. That means it cannot be solved in the polynomial time. But what is the speciality? But problems are checkable in polynomial time. You can verify the problem if the solution is given, but you can able to verify those solution is correct or not within the polynomial time. Say for an example, Sudoku game. Solving this game will require exponential time. The kind complexity for solving this particular game will be exponential time. But once a solution is given, then it is easy to check whether the given solution is correct or not. So always your solution verification is done within the polynomial time. So that is a speciality of the NP problems. Moving on to NP in depth, like this is based on many algorithms will be based on this NP, like divide and conquer algorithm, greedy algorithm, dynamic programming, exploring graph, branch and bound. So many number of strategy will be based on this NP. So as we discussed, the class is especially divided into two parts. One is polynomial time, another one is exponential time. Whatever the algorithm will come under polynomial time, searching and the sorting algorithm. Exponential time means the knapsack problem, traveling salesman problem, graph coloring problem. Those problems will come under. That means the problem you are finding for optimization problem. Like based on apart from optimization problem, everything will come under polynomial time. Once your problem is going to find out some optimization solution, optimization problem, then it will come under exponential time algorithm. Okay. So we always try to solve exponential time algorithm into polynomial time algorithm. Okay. So if we cannot write polynomial time algorithm for exponential time algorithm, then we can write non-deterministic algorithm. So that is the NP class algorithm. In deterministic algorithm, all the statements are clear. So what is the main difference between deterministic and non-deterministic? Whenever you are going for deterministic, the algorithm statements would be very much clear. Okay. But in case of non-deterministic, most of the statements would be clear, but some statements are not clear. Okay. Let me see one example how this is being, this will be matched with a non-deterministic algorithm. Okay. We'll move on to this searching algorithm. This is a searching algorithm which is given. Here we have a function called search underscore NP, and they pass an argument called key, and it contains an array list of 100. Okay. Now we have a term called I is equal to check underscore array of key. So this is a, like I is a variable. Wherever you find a key, that key, for example, you are giving some such element that you have to find out the, 100 elements are there in the list. So you have to find out in that within that 100 element, what is your search key element. Okay, so that element you found that you are storing in the variable I, and you are checking the index of the I and with the list of the list of element, and you are matching with the key element. So whenever your key and the list of array index of your element is matching, you're saying that search element is found at the index I. Else you are saying that searching is not found. So this is a simple logic which is given for searching. Okay, what is this? If you calculate the time complexity of this particular pseudocode, you'll get for storing array, it will take some, already it has been given some hundreds, or obviously it will take some constant time. And you're checking, you're having the key. Once you found the key, that key, index of the key are storing using the variable I. That also will take order of n1 complexity, time complexity. Then your comparison, doing comparison, that will take order of 1. If that works, if condition satisfied, then it will take order of 1. Else, otherwise, it will take order of 1. So the time complexity of the above algorithm is order of 1. So if you total it, you will get order of 1 only. But why come that? But why, this is a non-deterministic algorithm. Why? Because we say that whenever your time complexity is lesser than exponential time, obviously this will come under deterministic algorithm, right? But in case this is, even though this particular pseudocode is taking order of 1 time complexity, but we are calling it as why it is non-deterministic algorithm is, what is the thing is, here you can see in one statement, I is equal to check underscore array of key. We doesn't know what is this function, how this function is actually working. Okay, based on which criteria, which product, which method it is following. Like we are telling, we have to find out some search key from the list of 100 element. Directly they are getting the key elements, and it is being stored in the I value. So beyond this, at the beginning of this function, this method, how it is working, it is not at all given. Okay. So that is how this algorithm will take this will come under the non-deterministic algorithm for search. Okay, and we'll see a difference. What is the Venn diagram of the P and the non-P? So always P should be a subset of the NP problem. So in the past, if you talk about sequential search, it was the time complexity was order of n. Now, but in present, we got a time complexity of order of 1. Okay. In future, if you think now binary search algorithm, it takes some logarithmic order of logarithmic time algorithm, right? So maybe in future also, maybe if some better algorithm would come, that will take some better than this logarithmic time algorithm, right? Like we cannot predict it. Okay. So now it may be in deterministic, in non-deterministic. In future, it may become deterministic algorithm. Okay. So that is with the, maybe based on the research and the solution, maybe the algorithm class maybe varies. Okay. So moving on to NP hard and NP complete. This is a subdivision of NP problems. So to understand NP hard, so we first know what is a concept called reduction. Okay. It is very simple. You have some two decision problem, P1 and P2. So both having the input I1 and I2. But for the problem P1, algorithm is not exist. I have marked a question mark. That means algorithm is not exist for that particular problem. But for problem P2, algorithm is exist. The name of the algorithm is given as B. Okay. So what is our reduction is when we have algorithm for problem P2, with that help of problem P2 algorithm, can we able to solve, find out solution for the problem P1? Yes, that is the concept called reduction. Okay, so suppose we can say that problem P1, by using algorithm of problem P2, there is no need to write an algorithm for the A. That how you represent in the form of reduction is P1 is reducible to P2. Okay, so we can able to solve problem P1 with the help of an algorithm of problem P2. Okay, the conversion will take some polynomial time. Okay, so we no need to write an algorithm for A. Okay, with the help of B, if we can able to solve the problem, then no need to write an algorithm. Okay, this is the concept called reduction. Okay, let A and B are two problems in NP. If A is reduced to problem B, if there is a way to solve A by deterministic algorithm, that solve B polynomial. So that we can denote A reducible to B. Okay. Moving on to NP hard. So a problem is NP hard if all problems in NP or polynomial time reducible to it, even though it may not be in NP itself. Okay. You can see in the Venn diagram, in the left hand side, you have an NP problem. In the right hand side, you have NP hard problem X. If you have NP problem, that all problem can be reducible to it with the help of NP hard. Okay. So that is the relation between NP and NP hard problem. Moving on to NP complete. Any problem is NP complete. It should be a part of both NP as well as NP hard. So this is an intersection. NP complete is an intersection between your NP and the NP hard problems. We'll see overall Venn diagram of P, NP and NP hard and NP complete. So this is the overall. P is always a subset of NP problem and NP complete is an intersection between your NP and the NP hard problem. Okay, that is all about the computability of algorithms. Okay, thank you, please. Thank you.